Okay, so now we're finally going to start talking about covalent bonding and the differences between covalent bonding and ionic bonding. And though I might draw some metaphors between human relationships and covalent bonds, or any kind of bonding for that matter, we are not talking about dogs and puppy dogs and little girls. So covalent bonds, remember, are where electrons are being shared between atoms. And when we look at the theories of covalent bonding, you'll start to understand why a molecule will be arranged a certain way. As in water, the water molecule, it has that Mickey Mouse appearance. So in covalent bonding, just as in ionic bonding, atoms want to fill their outer shell and be happy or complete. And remember the octet rule, full valence shell of 8 electrons. So they're always shooting for 8 electrons in their outer shell, except for hydrogen and helium that are content with 2 outer electrons. So with covalent bonding, they're sharing bonds, sharing electrons, and that shared electron pair is called a bonding pair. And covalent bonding occurs between nonmetals. This is just a few examples. You have a methane molecule here. This is the basically the chemical formula for the methane molecule. This would be a structural formula. And then these are just 2 different models showing the orientation of the atoms to each other. So when we look at chemical bonding, we really need to start talking about attractive forces. And we study electronegativity a little bit in the trends of electronegativity as you look at the periodic table. But going back to those concepts of electronegativity and the electron configuration, these are really the driving forces behind bonding. So it's still important to understand that electron configuration, particularly with the valence electrons, those outer shell electrons. And with electronegativity, we'll start to look more specifically at the values for each atom and how that determines what type of bond will form, whether it'll be a covalent bond, an ionic bond, or something in between. So here's just a diagram of the periodic table showing the relative electronegativities of the elements, and you can see how in the upper right hand corner we have very high electronegativity values for these nonmetals, and then as we move across to the lower left hand corner you can see we have the lowest electronegativity values. So these atoms are not trying very hard to attract more electrons, whereas these atoms in this corner are trying to attract electrons, and you can see that hydrogen kind of falls into this category of higher electronegativities. The transition metals, again, that's the D block filling, and so we see a different kind of a pattern emerge within the transition metals, and we'll primarily be dealing with the main group elements that you see here. This is just a table of the electronegativities for the elements, and this is something that you can come back to for reference. So what we do to determine the type of bond that's going to form is you look at the difference in electronegativity between the atoms that are bonding. And remember again, as we look at all these rules and these patterns, that there's always going to be exceptions to these rules. So just keep that in mind, that you may run across some exceptions. So looking at the values, and again, these values represent the difference in electronegativities. So this first value here, the 0.0 to 0.4, represents a nonpolar covalent bond, which means that there's equal sharing of the electrons. So for example, in the hydrogen molecule here, the electrons that are being shared are equally attracted to both of the hydrogen nuclei. And again, this value represents the difference between the 2 electronegativities of the hydrogens. If we have a difference between 0.4 and 1, you're looking at a moderately polar covalent bond. And an example of that would be the hydrochloric acid molecule. And in this case, the chlorine end of the molecule is a slightly more negative than the hydrogen end of the molecule. And we'll look at some diagrams of this, and you'll see this in a little more detail. This value between 1 and 1.6 are very polar covalent, meaning they're really almost ionic in nature, that there is one atom that has a stronger pull on those electrons than the other atom. This example is incomplete. There should be another atom here. I think this is supposed to be hydrofluoric, possibly, where you would see a little bit an even stronger pull with the fluorine atom than you would here with the chlorine atom and hydrogen. So hydrogen and fluorine, you would see fluorine with having a stronger attraction for the electrons than the hydrogen. And then what would be greater than 1.7 would be an example of an ionic bond where the chlorine has the full attraction of those electrons, and sodium is actually losing an electron to the chlorine atom, forming ions that are then attracted to each other. So again, these values represent electronegativity differences, and you do have on all the cheat sheets that I've given you, you do have a table that lists these values on it. So we're just going to look real quickly here how chlorine forms a covalent bond with itself, and we'll use the Lewis dot structures to demonstrate that. So a chlorine molecule, and again, when I say molecule, I'm referring to atoms that are covalently bonded to each other. The chlorine molecule will have two chlorine atoms that both are trying to satisfy the octet rule. They both want A electrons in their outer shell. And so because the electronegativity difference between the two is going to be 0, because they have the same electronegativity, they have the same desire to attract electrons, they're going to exert an equal attraction on those shared electrons. So you can see in the dot structures that chlorine has 7 valence electrons, and each chlorine wants to gain 1 more electron to achieve the octet, and neither one of them is going to give up an electron because they have such high electronegativity values. So what we find is that they will end up sharing the 2 electrons here in the center. So chlorine is donating 1 electron to the shared pair. This chlorine is donating 1 electron to the shared pair. And we now see that this chlorine has its octet. This chlorine has its octet. And the octet is achieved by each atom sharing the electron pair in the middle. And they have, these electrons have an equal attraction to both the nuclei of both of those atoms. And there's our shared pair. So the bonding pair is the 2 electrons in the center, and this is referred to as a single bond. And sometimes this is written, usually this is written as the 2 element symbols with a dash between them. So single bonds are abbreviated with the dash. Oxygen is another diatomic molecule. Chlorine is a diatomic molecule. I'll point these out to you in class on the periodic table. How do the 2 oxygen atoms form? First, we write the Lewis dot structures. You can see that oxygen has 6 valence electrons, and so we show that there's a pair, 2 pairs on 2 sides, and then we have 2 single electrons here that need to be paired. So each atom has 2 unpaired electrons, and we're going to see that the oxygen atoms are both highly electronegative. They have equal electronegativity values, so the difference between them is 0. And they both want to gain electrons. Neither one is going to give up an electron, and therefore it's going to result in sharing of electrons. In this case, we see that oxygen shares both pairs of electrons, which gives the oxygen on the right its full octet of 8 electrons, and the oxygen on the left has the full octet of 8 electrons. And again, we have 2 bonding pairs that can be denoted by 2 dashes. Okay, so I'm not going to show it in this PowerPoint, but there is also a triple bond where you would have 3 shared pairs in the middle here. So there would be another pair of electrons, and you would abbreviate that with 3 dashes instead of 2. And so that's the oxygen molecule. Just a couple quick look at some of the properties of the covalent compounds. In comparison to ionic compounds, they have lower melting and boiling points than ionic compounds. There's distinct molecules held together by weaker intermolecular forces. So what that's saying is that if we have a sample of water here and you have all these water molecules that are held together fairly strongly within themselves, but then there's also a weaker intermolecular attraction between individual molecules, and those are held together by a weaker force than we see with formula units in an ionic compound. So there's the attraction of the molecule within itself, which is intramolecular, and then there's the attraction of one molecule to another molecule, which is intermolecular. Because of the weakness of that force, we see lower melting and boiling points. These compounds tend to be soft and squishy for the same reason covalent compounds tend to be flexible rather than rigid and hard. So the examples that I showed you of ionic compounds in class were all in a crystalline form. They were hard. Some of them were brittle. The covalent compounds we often see are gases and liquids, and soft and squishy is just kind of a nice way easy way to remember that. So covalent compounds tend to be more flammable. The combustion reaction, by definition, is a reaction that occurs with oxygen, typically between carbon and hydrogen atoms, or a carbon and hydrogen compound. And the products of that reaction are usually carbon dioxide and water in a complete reaction. Covalent compounds do not conduct electricity well at all. There are no ions present, no free electrons to move around, and they are generally insoluble in water. And we see this rule like dissolves like, which means that covalent compounds tend to be soluble in other covalent compounds, and ionic compounds or polar compounds will dissolve in things like water, which is a very polar compound itself. So, and we'll do some labs to explore some of these properties of covalent compounds, and we'll be looking at the differences between ionic and covalent compounds as well. So that ends this set of notes, and we'll talk about these more in class tomorrow.